Probabilities. So today it's a pleasure to have with us Marilena LaVerde. She's visiting from Colombia. She's finishing her PhD working with Lumpy. She has been working mostly on cosmology, gravitational lensing, and today she's going to tell us more about observing through Lumpy models.
Okay, thanks. So the title of my talk is Observations Through a Lumpy Universe, and what I mean by that is I'm going to talk about how observations that we make of distant galaxies and quasars are affected by the fact that we're looking through an inhomogeneous universe to see those distant galaxies and quasars. So specifically I'm going to talk about weak lensing, but how it affects measurements that we make of the galaxy distribution. So why do we want to make maps of the galaxy distribution anyways? Well, if we look out and we make a map of the distribution of galaxies, we can measure the galaxy clustering, and from measurements of the galaxy clustering, we can learn about how matter clusters. And if we make measurements of how matter clusters at different redshifts, we can learn about how structure evolves. And from learning about the growth rate of structure, this depends on the background evolution of the universe, so it depends on the matter contents. For example, if there's dark energy, a cosmological constant, or how much matter there is. We can also use measurements of the galaxy distribution to extract secondary anisotropies from the primary anisotropies in the CMB. Also, measurements of the galaxy clustering have special features which can be used as standard rulers, and with these standard rulers we can map out the expansion history of the universe if we measure them at different distances. So the reason that I'm interested in galaxy clustering in particular is to learn about cosmological parameters. So the outline of my talk is I'll first talk about cosmic magnification, which is the weak lensing effect that I'm interested in. Then I'll talk about how it affects the measurements of the integrated Sachs-Wolf effect, the angular power spectrum, the 3D correlation function, and if I have time, I'll talk about some work in progress on the limit torus. So what is cosmic magnification? Well, if we look out at a distant source, we observe that source by seeing the light that it emits that reaches us. But those photons that reach us have traveled through an inhomogeneous universe, and as they travel through these lumps of large-scale structure, their trajectories are deflected slightly. So maps that we make are distorted by this distortions in the trajectories. So if I'm making a flux-limited survey of the galaxy distribution, this has two effects. One effect is to bring more photons into the line of sight, which causes the sources to appear brighter. And another effect is to increase the area of the patch of sky that I'm observing, so that I see fewer sources. So together these effects lead to a correction to fluctuations in the number density. The increase in area decreases the apparent number density behind regions with positive magnification. And the brightening effect promotes intrinsically faint objects, which are otherwise below my magnitude threshold, into my survey. So this causes an increase in fluctuations in the number density. So this is just a head-on picture of this effect. Here I'm looking at some galaxies. The effect of lensing is to spread out the patch and to bring these new sources into my survey. So this is a well-known effect that many people here work on. So the correction to fluctuations in the number density is called magnification bias. So I'll use this a lot. What this delta n is fluctuations in the observed number density of galaxies, and it has two terms. One is the true fluctuation, or the intrinsic galaxy fluctuation, and the second is this correction due to magnification. So the effect of magnification depends on the population of galaxies, and it does because it depends on the slope of the number count function. So why does it depend on the slope of the galaxy number count function? Well, the effect of lensing is to lower the magnitude threshold of my survey. So if I'm observing, if my limiting magnitude is on a flat part of the luminosity function, then lowering my effective magnitude by a small amount will bring fewer new galaxies into the survey than if my limiting magnitude is on a steep part of the galaxy luminosity function, and changing the limiting magnitude by a small amount will bring many more galaxies into the survey.
Can magnification bias be negative?
Yes. I'll show you. So it can be negative because there's the competing effects, the dilution due to the area increase and bringing new sources in. And they can also cancel each other if the slope of the luminosity function is exactly flat. So it also depends on redshift. Now if I'm looking at high redshift sources, which are illustrated by this blue curve, these sources are being lensed by stuff all along the line of sight, and that's illustrated by this red curve here. So if I'm observing some at high redshift, it depends correction depends on the redshift of the sources. As I go to higher redshifts, there's more stuff along the line of sight, and there's a geometric effect which makes the effect of lensing larger, which is illustrated by the same source distribution at different redshifts. I have a larger lensing weight function, which can be thought of the probability distribution for lensing as a function of redshift. And here, showing again how the intrinsic fluctuations in the galaxy number density depend on the fluctuations in the mass, which in a linear regime can be assumed to be proportional by some linear bias factor. The magnification correction depends on the number count slope. It also depends on the mass along the line of sight, but here it has an overall proportionality that depends on the number count slope. So you can see if S is equal to 2/5, that cancels. And just to be clear, the lensing correction depends on the mass along the line of sight, but it's not exactly proportional. It's actually an integral over all the mass fluctuations along the line of sight with this lensing weight function here. So how big is this number 5s minus 2 over b, which is going to tell me how large the lensing correction is. So here, just to illustrate, are some example values of this function 5s minus 2 divided by b for different limiting magnitude cuts of surveys. So what we've done here is take real luminosity functions and use a theoretical model for the galaxy bias. So these aren't measurements, but it's the point is to show that this parameter can range between -1 and 2, and it's larger for brighter populations of galaxies. So magnification bias adds a redshift, scale, and galaxy population dependent correction to the observed galaxy fluctuation. What are the effects of this on integrated stack-Wolf effects? Features in the angular power spectrum and the 3D correlation function. So now we'll talk about the integrated Sachs-Wolf effect. So what's the integrated Sachs-Wolf effect? Well, a photon that's traveling through the universe travels through a lumpy universe with lots of gravitational potentials. A photon falling into a gravitational potential is going to be blue shifted, but when it climbs out of the potential, it's going to be red shifted again. So as long as this potential isn't changing, there's no net change in the photon energy. However, if the gravitational potential is changing with time, for example, it's decaying, the photon climbs out of a shallower potential than it fell into, so it experiences a net change in energy. So we have the CMB, which has lots of photons traveling towards us through all of these different potentials. And this is very interesting because in a universe that's not Einstein de Sitter, it has any contributions from cosmological constants or curvature or anything other than cold dark matter, the gravitational potentials decay. So that means that in a universe that's not exactly matter dominated, there's going to be a secondary anisotropy and a CMB. And the secondary anisotropy is a signature of, if we think the universe is flat, something like dark energy domination. So this is a useful tool to learn about when the onset of dark energy domination takes over. So how do we learn about the integrated Sachs-Wolf effect, the secondary anisotropy, by looking at the CMB? We want to separate the secondary anisotropy from the primary anisotropies of the surface of last scattering. And we can do this because only the photons that come through gravitational potentials during the dark energy dominated era are going to pick up the ISW effect. So that means that tracers of gravitational potentials like galaxies can be correlated with the CMB, and we expect there to be a correlation for a universe that has decaying potentials. Another way I like to think about that is that when we see the CMB, we look out in all different directions and we measure temperature anisotropies, but we only have information about the angle. So what's the temperature fluctuation here compared to here? We don't have any information about the time dependence of how those anisotropies were laid down. But if I'm correlating the CMB with galaxies at some redshift, I'm asking the question, what was the anisotropy that was put down at the redshift of the galaxies? So in the case of the ISW effect, I'm asking the question, on this plot is shown the change in the growth rate, which is how potentials are changing with time as a function of redshift. You can see as I go to high redshift, this is for several different values of the equation of state parameter, W. As I go to high redshift, this curve is small in all of these cases. But when I transition from having small derivative of potentials to a larger one depends on the value of W. And correlating galaxies with the CMB, if I correlate galaxies with the CMB at redshift 1, I'm asking the question, what is the derivative of the growth function at the redshift of those galaxies? So that's how I'm extracting that information. And it's a particularly useful tool because you can move your galaxies back and forth and determine the onset of some information about the onset of acceleration. So a number of measurements of the ISW effect have been done. There's actually a number of more recent measurements that I'm showing here. But just to illustrate information from the ISW effect is measuring something about growth of structure. So it's complementary, as shown in this parameter plane, to stuff that's learned from supernova data. So what happens if we include lensing magnification? So now I'm showing that same plot that I had on the page before. I'm showing the derivative of the growth function in this black dashed line for lambda CDM cosmology. And in blue, I have the source distribution. So galaxy fluctuation depends on the mass fluctuation integrated over some source distribution. And in red, I'm showing something like the lens distribution. So the lensing correction depends on the mass fluctuation integrated over some other distribution, which is shown in red. So if I look at these different curves, you say, well, this red curve is always a lot smaller than the blue one, so the effect of lensing is probably quite small. But the fact is, these two curves are unequally weighted. So as I move my galaxies to high redshift, the derivative of the growth function is small, so there's no ISW effect, and I see a small cross-correlation signal. On the other hand, for galaxies at very high redshift, the lenses, these galaxies are at high redshift in a nearly matter-dominated universe. The lenses are still at lower redshift in the dark energy-dominated universe. So the lensing temperature correlation can actually be large compared to the galaxy temperature correlation. So with magnification bias, the cross-correlation is a sum of two terms. This is the temperature fluctuation, and this is the observed fluctuation in the number density of galaxies. The first term has information about the growth rates of structure at the redshift of the galaxy sample, and it depends on the galaxy bias. The second term has information about the growth rates of structure, but not at the redshift of the galaxies, but at the redshifts of the lenses, which are at lower redshift. And it depends on the slope of this number count function. So the relative magnitude of these two terms is going to be redshift dependent, because lensing grows with redshift. It's going to be galaxy population dependent because of the slope and bias factor. And it's going to be scale dependent because this term, the lenses, is probing structure at different distances than the galaxy does. So stuff which is nearer to us occupies a larger angular scale. So the scale dependence of those two terms is different. So how would magnification bias affect ISW measurements from something like an LSST survey? So here are some plots illustrating. This is the angular power spectrum of the galaxy temperature cross-correlation. The blue curves ignore lensing, and the red curves include it. The difference between these two plots is I'm taking two different samples of galaxies. This is all the galaxies, our estimate for our estimates of the bias and the slope luminosity function, and this would be a bright subsample, which might be analogous to the LRGs. So these measurements are at redshift of about 1/2, and here you can see the effective lensing is quite small. But if I go to higher redshifts, the whole cross-correlation signal drops off because I'm looking at stuff nearer to the matter-dominated universe. But the effective lensing grows, and it can actually be quite large. So here at the highest redshift, redshift 3.5, the difference between including lensing and ignoring it is quite significant in both of these cases. Even here, the whole signal is small, but the correction is still of order 100%. So what's happening? The intrinsic galaxy temperature cross-correlation is dropping off, but the lenses are still in the dark energy-dominated universe. So there's a large cross-correlation signal, which changes the amplitude of this, and it also shifts the location of the peak. So clearly, this is a big effect. But what if we decided to ignore it anyways and do measurements? So this plot shows a thought experiment. Suppose that the universe is dominated by a cosmological constant which has an equation of state, W equals to -1. And suppose we do ISW measurements on all those plots that I showed and interpret the data ignoring lensing. What you see, what value would we get for the inferred for W? What value would we infer from our measurements? So you can see what's shown here are these different data points show the value of W you get from each different redshift bin and the error on that redshift bin. In both cases, at high redshifts, you see a value of W which is not equal to the true value in the spot experiment, which is -1. And for the bright sample, you see a large cross-correlation at very high redshifts, and you infer quite precisely, because you have a large signal, that the value of W is something like -0.6. If I average all these redshift bins together, I get these dotted lines here. In the case of the full sample, it doesn't make a very big difference at all, but for the bright sample, which has a larger effect of lensing, it makes quite a big difference. So you infer the wrong value of W, and you assume that your measurement was very precise.
Where do the sizes of error bars come from? Like, why does the all sample have larger error bars than the white sample, even though there are presumably more galaxies in the all sample than the white?
There's more galaxies, but the effect here of lensing is much larger, so it boosts. Because in this spot experiment, I'm ignoring lensing, so I'm ignoring the covariance between bins, I think that I have a larger ISW effect. There's, because the cross-correlation signal appears larger because of lensing. And if there's appears to be a larger signal, then I have a large signal at more redshifts.
Is that based with an LST number distribution? Or
yeah, yeah. But so there are 2 points to take away from this. One is that you infer the wrong value of W, and you also think that you have better precision on your measurements than you do. So I'll show a plot in a second that might make more sense. That might make this make more sense. If it doesn't,
based on cross-correlation with W map, or I mean, what exactly goes into here? Because the W map noise parameters, or the tank noise parameters, and the LST.
Yeah, it's this is something like W map, but we're not taking into account. We have not taken into account all the noise from the CMB. This is just assuming that the noise is it's something like the temperature autocorrelation and the galaxy plus some Poisson noise term. There's probably other noise terms that should go into here as well. This is just, but this is just to compare with and without lensing. So in both cases, it's a simplified analysis. So with lensing, you have this large signal out to high redshifts. So does that mean that we have a large signal at other redshifts that we can actually go out and measure and learn something from? And what's shown here is the signal to noise in each of the redshift bins for both galaxy samples. And this is ignoring lensing. You can see if I ignore lensing, the signal drops off with redshift, which is what you expect, because there's no ISW effect out here, unless something funny is going on that we don't know about. But if you include lensing, there's actually a large signal to noise out to high redshifts, and particularly for this bright subsample. So it appears, I think you can see on this plot that the signal to noise is larger for the bright sample because of lensing. But this is
you scale here. So signal to noise squared of 10 means about just under 3 sigmas. That's how I read that graph.
Yeah, that's right. So it's this is for half sky, something like LSST, 10 a billion galaxies, billions of galaxies observed over half the sky. So ISW measurements don't have high signal to noise very much, anyways. So it appears that having lensing gives you a high signal to noise out to large redshifts. So it, on the one hand, this opens up a new window to doing high redshift ISW measurements. But of course, these high redshift measurements are really strongly correlated with the low redshift ones, because out here, I'm really just measuring structure due to the lenses, which is at this low redshift. So if I've done ISW measurements at all those lower redshifts, doing the high redshift measurements doesn't add much to them. And that's what's shown here. Instead of the signal to noise in each bin, this is the cumulative signal to noise as a function of the maximum redshift that I'm including. Okay? So in this case, as I go to higher redshift, I get more and more information. But at some point, the signal levels off, because there's just not an ISW effect out here anymore. And in this case, the difference between lensing and no lensing is not very large. autocorrelation is very strongly correlated with lower redshift measurements of galaxy temperature correlation. So it's not expected to provide much new information, but one thing is that the magnification temperature correlation doesn't depend on galaxy bias, which is often uncertain. So in some sense, it's a more accurate tracer of the mass temperature correlation, which is what you would truly want for a galaxy temperature measurement. So now I'm going to talk a little bit about how magnification affects the shape of the angular power spectrum. So here's the angular power spectrum, just the...
Could we just go back to...
Yeah.
What about things like subselection on the galaxies that are getting biased so that you might, they're providing the magnification bias? Don't worry about that.
Okay, sorry. I can't quite hear what you're saying there.
What about doing subselection? I mean, there are many ways. I mean, maybe this is a good effect,
Yeah.
but there might also be ways to normalize it out by doing a different definition of what your statistic is for the ISW effect.
That's right. So I'm not sure if this is what you're saying, but one way that you can get around this is by choosing a subsample of galaxies, which has a flat slope of luminosity function, so there's no magnification. Another way would be to look at different subsamples, which have a different slope and weight it. Yeah. So that's how people have done detections of magnification have, thus far, I think, relied on people looking at galaxy quasar lensing and weighting the measurements by looking at different subsamples of quasars with different slopes and weighting them to extract the magnification signal.
You mean to short it out?
No, in this case, to detect it. So depending on the value of that slope, you have more or less magnification.
So the other thing which I wasn't quite clear on, generally with a weak lensing effect, it's infinitely computable.
What do you mean?
You can compute it without any problem at all, but this one involves some more information about population and the weak lensing without the amplification taken into account.
You mean like shear or something?
No, it's just that you've got to know something about a lot of details about the model
Of
population.
galaxies. Yeah. I mean, I haven't done any good analysis, but my understanding is that something like the slope of the number count function is a lot easier to measure than the galaxy bias, for example.
Okay. It's just, can I put this into a code with very simple factors and get out a unique solution to exactly what this is going to look like, or does it depend upon specific details of the assumed luminosity function for the source?
So it depends on the luminosity function, but only the slope at one point. But actually, the most recent measurements of by Shirley Ho and Masurata and others include the most recent measurements of ISW effects actually include magnification. Now, does that answer your question?
More.
Okay. So now I'm going to talk about the angular power spectrum, by which I just mean the autocorrelation function of the galaxy fluctuation. If you're used to thinking about the 3D correlation function, or 3D power spectrum, the angular power spectrum is just an integral over the 3D power spectrum over some redshift distribution. And if there's some feature in the 3D power spectrum at scale k, that'll show up in the angular power spectrum at a multipole moment L, which depends on the distance to your sources that you're looking at. So here's a plot of the angular power spectrum. So I said I was going to talk about features in the angular power spectrum. What are features that I care about? Well, one feature that I might care about is the location of this peak, the turnover in the power spectrum. So this peak separates modes which enter the horizon during radiation domination from those and had a drop in amplitude to those modes which entered the horizon during matter domination. So the scale of this peak, K equality, just depends on the horizon size and matter radiation equality, and that's something that we can calculate. So the location of this peak is a predictable scale. There are also these small baryon oscillations here, which are just like the baryon oscillations in the CMB, but suppressed. And the scale of the location of these oscillations just depends on the horizon, the sound horizon at the time when photons decoupled from baryons early on. So those are some features that I'm interested in. But why do I care about features? Well, these are features of known size. So So let's think about a cow, which is an object of known size instead for a second. If I know how big this cow is, and I measure the angular size of the cow, I can determine how far the cow is away from me. So this is exactly what people want to do with these features in the angular power spectrum. They're objects of known size, which we measure at different redshifts. By observing the angular scale of these features, we can determine the distance between us and the redshift of the correlation that we're looking at. So if I include lensing, the autocorrelation function now is a sum of 4 terms. I have the intrinsic galaxy correlation, I have the lensing correlation, and then I have these cross terms that between the galaxy fluctuation and the lenses. So here's just an illustration of that. The effective lensing is going to depend on the width of my source distribution. So here I have a narrow source distribution and a broad source distribution, and I've plotted, for both cases, the distribution of lenses, which you can see doesn't change very much if I change between narrow and broad source distributions. But what does change is the overlap between the sources and the lenses. And this also depends on the redshift. As I move my sources to higher redshift, the effective lensing grows, and the difference between the overlap of these two also changes. So here's a plot of the angular power spectrum. The blue curve is the galaxy auto power spectrum. The purple one is the cross power spectrum between galaxies and lenses. So you can see, and the red one is the lensing auto power spectrum. So these look just like we would expect them to. If I look at these different distributions, the galaxy lensing cross term depends on the overlap here. So it's measuring the mass power spectrum at a redshift which is similar to the redshift of the galaxies we're looking at. So we expect the shape of the power spectra to be the same, but just suppressed in amplitude. The lenses, on the other hand, are measuring mass fluctuations over a very broad range of redshifts. So, and it's also peaked at a much lower redshift. So what you see here, this term depends on structure, which is much nearer to us, so occupies larger angular scales, and it's peaked at lower L. Also, because it was such a slowly varying function, fine features like the baryon bumps have been washed out. So what's the effect? Well, these corrections look small compared to the auto power spectrum, but if you want to know exactly where, for example, the location of the matter radiation equality peak is, it might matter. So here's some plots of the angular power spectrum again, but because I care about the shape of it, what I've done is divide it out by an angular power spectrum that neglects the effects of baryons that create those oscillations. So here's narrow and broad source distributions. You can see with the broad source distribution, the effect of lensing is already quite large. And as you go to higher and higher redshifts, it becomes larger and larger, and it's particularly more dramatic if you look at very low L. So that's
that's just the ratio of the plot in the previous slide. Is that what you're plotting here?
sorry.
So this
This is
the red curve compared to the dotted magenta curve is just equal to the on the previous slide the power spectrum minus the galaxy minus lensing. Is that what you're plotting here?
what I'm plotting the red curve. So in both of these plots, sorry, I don't want to show. I'm showing the red is the total cross power spectrum, and the blue one is just this. And in both cases, I've divided out. So there are these baryon oscillations. I've divided out by a no baryon power spectrum. They're the same one.
But in the previous slide, the lensing only contributed to maybe a few percent of the total power. So I'm trying to see why it becomes a factor of 2 when you subtract the 10% effect. Yeah, here. This
So this is
never
what
more
it,
than 10%.
that's right. But so what's the difference between all these plots here? Here the effect is never more than 10% either. But I'm looking at low redshift. The effect becomes larger as I go to higher redshift. So that was just looking at a particular low redshift thing.
I see.
Does that make sense?
Is this
Yeah.
assuming a linear power spectrum? Because I would assume that nonlinear growth would wash out the acoustic oscillations on large, small angular scales, large L. And I don't see this here.
That's right. This is the galaxies are at higher redshift and further into the linear regime. So the fact that you have, there's an extra boost in the lensing because it is at lower redshifts and has more nonlinear evolution. Does that answer your question? Okay, so I started out by saying that I cared about the shape of the angular power spectrum and features, so now I'm zooming in on the peak in the angular power spectrum, the amount of radiation equality peak, and it's hard to see from looking at these plots whether lensing, certainly it changes the overall amplitude, but does it actually move the location of this peak very much? Well, it can, but it depends on how broad of a source distribution you're looking at. So these are for sort of narrow, very broad, and just right distributions of sources. At low redshifts, there's not much of an effect, but by high redshifts, in all cases, the location of the peak is shifted by a non-negligible amount. So the location of the matter radiation equality peak at these redshifts is like L of 70 or something. So it's a non-negligible shift. The thing to keep in mind about all of this is that the effect of, so we also looked at, for example, the baryon bump, but the thing to keep in mind is that lensing is adding a scale-dependent correction to measurements, and lensing is adding a scale-dependent correction to your correlation function, and real measurements will involve fitting data with error bars, and what the real effect of lensing would be to these features will depend on how they're fit in the data. So now we want to talk about how lensing affects the 3D correlation function. So the 3D correlation function is a measure of if So suppose I have a fluctuation of mass here. If I'm some distance r away, what's the excess probability above random that there's also going to be a fluctuation in mass there, or for example, a galaxy? Well, if the universe is statistically homogeneous, then this quantity, the correlation, doesn't depend on where the 2 points I'm looking at are. And if it's statistically isotropic, then I don't care about the orientation of the 2 points that I'm looking at. The correlation function does drop off very rapidly with increasing distance between the 2 points I'm looking at. Ways of measuring this are, for example, averaging over galaxy pair separations. So now what happens if we include lensing? Well, galaxy pairs, which are oriented along the line of sight, can lens each other. And the effect of lensing is largest for a lens which is halfway between the observer and the source. So the galaxy, so if this galaxy is lensing this galaxy, the correlation between them can be quite large, even if the separation, even if those galaxies are separated by a large distance. So magnification bias will also affect the 3D correlation function, and this was first pointed out by Matsubara. Now, galaxies which are oriented transverse to the line of sight can't lens each other. So this means that lensing introduces an anisotropy into the correlation function, which, neglecting other effects like redshift-based distortion, would otherwise be anisotropic. So here's some plots of the 3D correlation function. Since the correlation function is anisotropic, what's shown here is a contour plot. This, on the x-axis, is the line of sight, is the transverse to the line of sight separation, and on the y-axis is the line of sight separation. So if there were no lensing, or if this was isotropic, this would be symmetric under exchanging those two axes. And this is just a contour plot of the correlation. So the correlation is large at small distances and drops off as you go to large distances. The solid curves here include lensing while the dotted ones ignore it. At this redshift, you can't see very much difference between including and ignoring lensing. If I go to higher redshifts, you start to see a more and more dramatic effect. Okay? The effect of lensing distorts the angular correlation function. The largest distortions are for small transverse separations, which makes sense because if I have small transverse separations, there can be lensing going on between the two sources that I'm looking at. And the biggest effect is at large line of sight separations. Okay, so going to increasingly high redshifts, you see a more and more dramatic effect and a larger breaking of the isotropy, and the effect of lensing becomes less confined to these small transverse separations.
This this assumes a luminosity function for the galaxies.
That's right. This assumes that here we've set that 5s minus 2 divided by b just equal to 1. So, so you would scale the effect of lensing correspondingly to something else.
But for example, like, well, for example, but things like also in the previous part, things like LSST, most of the galaxies I thought are in the negative magnification regime.
Right.
So the sign would actually reverse.
That's right. This is just, we're just illustrating what the effect could be and taking from that plot I showed you earlier of 5s minus 2 divided by b. It's not unreasonable to think that number could be about 1. But the true effect would depend on the population of galaxies. And it could be 0 if they had a shallow enough slope, or it could be negative. So let's think a little bit about the lensing anisotropy and think if we can understand it a little bit better. So the observed correlation function with lensing is the sum of 3 terms. The first is the galaxy-galaxy correlation, which doesn't care if I'm looking along the line of sight or if I'm looking transverse the line of sight. So this function is isotropic in those 2 parameters. And then I have the 2 lensing terms, which depend separately on line of sight separation and transverse to the line of sight separation. So, like I said, the first term is isotropic, and it drops off very rapidly with increasing transverse distance or line of sight distance. Now, I'm going to make an approximation that the separations along the line of sight and transverse to the line of sight that I'm looking at are much smaller than the distance between me and the sources. And if you do that, you can get a particularly nice expression for the lensing corrections. The galaxy lensing term drops off very rapidly with increasing transverse separation, just like this term does. But because of this effect of lensing, pairs oriented along the line of sight can lens each other. This term increases linearly with line of sight separation. So this is very surprising because this term is dropping very rapidly, but this one actually grows if you're looking at things that are further away from each other. And the lensing term also drops off with increasing transverse separation. But if I'm looking at stuff which is far from me, it doesn't really care about how large the line of sight separation is. Okay? So this is really interesting. What's shown here is a plot of the correlation function as a function of the line of sight separation for 2 different values of x perpendicular, the transverse to the line of sight separation. So the effect of lensing is illustrated by this black dotted line here, and the total correlation is the solid line. So if I'm looking at stuff with a small transverse separation, the effect of lensing is really large. It's quite dramatic. But because of that argument I just made, this means that in principle, the different terms, the galaxy-galaxy, the galaxy lensing, and the lensing-lensing term are separable. I can look at this plot, and this is the lensing correction shown in this black dotted line. The term which is linear in line of sight separation is proportional to the galaxy lensing cross term. The intercept of that just depends on the lensing term. So this means this is not meant to be a method for separating this term. It's just meant to illustrate that because of the particularly simple dependences, in principle, it might be possible to measure the anisotropic correlation function and isolate those contributions. So if that was possible, that would give you a way to measure separately galaxy-galaxy, galaxy lensing, and lensing power spectra without knowing about the galaxy shapes. So one thing that people care a lot about in the correlation function is the location of the acoustic peak. So that series of wiggles in the CME or angular or audit power spectrum shows up as a single bump in real space, in the real space correlation function. And the location of this bump depends on the co-moving size of the sound horizon at the couplet. So we can use this bump as a standard ruler. So the question is, this lensing adds large corrections to the correlation function. Does it move around or distort the location of this peak? So what's shown here, I've changed coordinates. This is the correlation function as a function of separation, and it's plotted for different orientations of that separation vector. So if theta is equal to 0, that means I'm looking exactly along the line of sight where the effective lensing is largest, which is shown as this curve right here. If theta is 90 degrees, I'm looking transverse to the line of sight where the lensing is smallest. So this little plot here shows the ratio of the observed correlation function, including lensing, to the ignoring lensing correlation function near the baryon bump. For separation transverse to the line of sight, the effect is small of lensing, but as I move that separation vector closer and closer to along the line of sight, the effect of lensing becomes much larger.
How would you, in practice, manage to keep the fixed physical separation when you do analysis of the data? Why it's not a fixed angle separation?
Well, I guess I imagine that you would need to measure the full anisotropic correlation function, and there would be error on angle and physical separation. This is just meant to understand how the lensing terms work, more than say what anyone would particularly measure. So there are lots of ways of measuring the location of the baryon bump. So instead of using all of those different ways as to how people fit the baryon peak, we just looked at a few quantities, like the peak height, which probably isn't so important, the peak width, which might be important because if the peak is broadened, then it's harder to find the maximum, and the peak location, which is the most important thing. So what's shown here is looking at the line of sight correlation function, the largest effective lensing. The shift in the peak location, width, and height as a function of 5s minus 2 divided by b, this galaxy population dependent quantity that tells you how big lensing is. And the different curves are for different redshifts. So the shift in the peak location can be, doesn't depend so much on the redshift of your sources, and it can be as large as 2%, which sounds quite small, but a 2% shift in the location of the peak leads to like a 5 or 10% change in the value of W, the equation of state parameter that you get.
What is the definition of peak location?
Where the maximum is in that function. So probably people won't measure the anisotropic correlation function, but what you might do instead is measure the monopole, so average over different angular directions. And in this case, the shift in the peak location is much smaller. It's less than 1% for all these redshifts and all of these values of 5s minus 2. But the broadening of the peak is still non-negligible. And again, what's shown here is the correlation function, the monopole. And on this plot, it's shown the correction due to lensing in the monopole. Notice the scales here are different. But the point is that there's a slowly varying scale dependence and galaxy population dependent curve that you're adding to this. And if you have noisy data, this might make a difference. Finally, one exciting thing is that just this summer, Enrique Gazzaniga and his student Ana Cabre and Lam made a measurement of the anisotropic galaxy correlation function from Sloan data. So what's shown here is a contour plot of the correlation function. This is the transverse separation, and this is the line of sight separation. So what you see here is, what I want to draw your attention to is the fact that the correlation function is anisotropic, but it's enhanced along the line of sight. And the enhancement along the line of sight grows with increasing line of sight distance. And they attribute this enhanced correlation to being due to magnification bias. So magnification boosts the signal. Can this boost in signal be used to our advantage? Well, maybe.
Can you go back to their result for a
Yeah.
second? So what is the quantitative number that you can draw from that contour map that says this is magnification bias, and at what
I don't think you can
what
just look at this
amplitude?
contour plot and say that that's magnification
No, but then
bias.
you can
but
reduce it to some presumably single number to say relative to expectation what you've actually found.
So they attribute it, I don't know what the single number is, but they attribute the fact that, so if you look here, you do see, as I look closer and closer to directly along the line of sight, the signal is increased. And the boost, you can't see it just from this contour plot, but the way how this amplification and signal increases with this distance is what sets them to attribute this to magnification. So you remember that the
And so
lensing
it's
I
not
showed,
a-
it's roughly like a linear term
So it's
that
not
you're
exactly
adding.
the right pattern as well?
So if they've taken into account redshift-based distortions properly, this should be closer to isotropic, or if anything, you would expect a weaker signal along the line of sight than transverse to the line of sight.
No, but surely they must have commented on the amount of magnification is consistent with what we expected or not.
Do they fit the model to the data?
They have they have simulations, and they look at what they expect the anisotropic correlation function to look like, including lensing, and they say that their data is consistent with this.
And
I'm not-
inconsistent with not including it.
I'm not sure.
I mean, this is just saying that you've measured galaxy magnification lensing instead of galaxy quasar. So this is the same measurement as wasted, except you use pairs of galaxies instead of pairs of galaxy quasar. Right? So this is that.
Well, that's right, but the separation is smaller between, this is stuff that's separated by smaller line of sight separations. The galaxies and quasars are separated by
That's
more
right.
than
That's
100
the scale.
megaparsecs.
That's the scale. So what we measure is a factor of 10 further separation than this effect, which is why it's much bigger.
But it also means that you don't have what he measured wouldn't have this term, for example. It would just be the galaxy lensing overlap. This includes the autocorrelation function. So taking the fact that magnification boosts the signal, maybe this enhanced signal can be used to measure stuff. And if you have, this is I've ignored lots of complicated things in writing this, but very roughly, the signal to noise goes like this correlation function here over the same stuff with the correlation function, but I have a term due to Poisson noise. So if this term due to Poisson noise is small, then boosting the signal by having magnification boosts this noise term too, so it doesn't help you. But if you have a sample which is not densely sampled, then you have large contributions from shot noise, then these boosts and signal from magnification can be of use. And in fact, this was put to use in that plot that I just showed you by Enrique and Ana and Lam. They used the fact that the signal is enhanced in the line of sight direction to measure. They have a shot noise dominated sample of galaxies. The correlation function is enhanced in the line of sight direction. And so they were able to get the first measurements of the Hubble parameter from the line of sight baryon bump. So what's shown here are those two data points measuring the line of sight baryon bump and the inferred Hubble parameter from that. So lensing magnification creates anisotropy in the 3D correlation function. The scaling of the different terms, galaxy-galaxy, galaxy lensing, and lensing-lensing, allows, in principle, for those terms to be separated. But in terms of doing precision cosmology, lensing adds something that's scale and galaxy population dependent to the observed 3D correlation function. And this should be taken into account to use the baryon bump for precision cosmology. So I have a few more minutes. Briefly, magnification also affects the 3D power spectrum, but the effect is somewhat qualitatively different to what happens in real space. The effect of this anisotropy that I talked about, I've completely ignored everything. In what I've said so far, I've completely ignored anisotropy due to redshift space distortions. If you include that, lensing is similar to redshift space distortions in that it introduces anisotropy into the correlation function, but the shape of the anisotropy is different, and it survives redshift space distortions. I think I'm going to skip this last part, although I'm enough before this. So magnification for making observations through an inhomogeneous universe adds challenges because observables are now affected, and when we think we're measuring structure at some at the redshift of our galaxies, we're also learning about structure all along the line of sight. If it's ignored, measurements can be quite biased. And precision measurements will require including the effects of lensing. On the other hand, the lensing signal does depend on cosmology. It depends on distances, and it has information about large-scale structure. So it might allow for new things to be measured. For example, high redshift measurements of the ISW effect, or this boost in signal can help if you have a Poisson-limited sample, like that Hubble parameter measurement I showed you. And this argument would also apply to the ISW effect if you had lensing-dominated measurements that have large contributions to shock noise, or possibly independent determination of those different terms.
Okay, questions?
I guess I was going back, so in Zhang and Pen, when we looked at the magnification, we were arguing that, well, the way you would disentangle magnification from the variance, I mean, yes, angle does matter, but that's a very weak signal. You're searching for counting to big numbers to see a small signal. If you just include the luminosity dependence and just say that I know how this depends on luminosity, you can almost perfectly orthogonally deproject the intrinsic clustering of the lensing. So before you even get to the angular part, you already deprojected, and then you just get a uncontaminated 3D and uncontaminated lensing signal without having to worry about angles.
I mean, it's a little bit, so those terms depend differently. I mean, the cross term that you have depends on this, whereas this term depends on that square. So it's not exactly, I mean, this can be negative and this can be positive, but they both have
just need three bins, just need three luminosity bins, right? So one at the zero crossing of the split function, there's no such term.
Sure.
And then in the other two terms, so, because you have at least three luminosity bins and you've got three unknowns, you can solve for all three before you do the angle problem.
Yeah, that's a good point.
Any other question? Can you come back to the definition of the control parameters?
Yes.
You just explain again how they fit.
So this is just from measuring, if you measure the acoustic scale and the line of sight direction, I mean, you know this, right? So that's not going to change. So measuring the location and the line of sight direction, that just depends on the physical scale that you measure. It just depends on the Hubble parameter along that line of sight. So other times when people have looked at the baryon bump, they measure some combination of H inverse angular diameter distance, just squared all to the 1/3. You have line of sight or transverse to line of sight summation of the angular diameter distance.
And so that's based on so we have we are using LRG.
Yeah.
Okay, so we have
Yeah, I don't think you would see the line of sight baryon bump unless you had spectroscopic redshift.
But going to this, so if I then project back to redshift 0 for this says that radio baryon acoustic oscillations are much better than anything that was done for those decades of work on varying receptors, etc. Is that what I'm inferring from this figure?
You mean measuring the
Well,
Hubble
look at the error
parameter
bar.
at 0?
I'm saying look at the error bar. I mean, it's just like you're blowing away poor Wendy Friedman's effort of decades and decades.
I'm not sure.
So I guess this question is saying, are those error bars really so believable? Because it's actually quite spectacular. Or are they conditioned on other information?
Well, the principle at all doesn't have similar size error bars, right?
So that
The principle at all also measures the Hubble parameter with a similar size error. It's just I'm surprised that if you shrink
I
yourself to only weight
don't know
pairs.
what, first of all,
It's the LRG.
yeah, okay, so that's
Just
using VAO
Yeah.
is better than everything that has been done.
Pretty much, isn't it?
Wow, great.
It's just surprising that
almost anything together with WMAP is better than HST. Ah, right, okay. Well, but this is actually including WMAP and its information on H. The information from H from WMAP, because that's a totally different story.
I guess they include it.
It's only included the information, the curvature from WMAP. So that's basically, that gives you only the curvature constraint, and the WMAP plus supernova, that gives you the different. So this brings basically the error bar in H naught without any other
The length of the ruler
say again?
is coming from WMAP.
That's exactly, yes. The ruler. So that's the physics error.
Okay, but the critical point here is that the amount of extra information beyond BAO is enormous that's being put into this measurement with the small error bar.